Hello, everybody. This is for section 3.8 in the OpenStax book, and it's on implicit differentiation. As you have just seen, my presentation of section 3.7 was very brief because most of the things you see in section 3.7 can be done once you learn implicit differentiation. It is a powerful tool. Many people don't like this first. In fact, as a student, I really didn't understand it and really didn't quite get it. But it doesn't really take that long to understand this concept, and it's going to give us an entirely new tool to figure out the derivatives of many other functions that we have yet to see. So let's look at this idea or the technique or skill called implicit differentiation in section 3.8. All right, the word implicit is, of course, the opposite of explicit, right? So we're going to be using some explicit language in this video. Please be aware. No, not really. Explicit differentiation is what we have been doing, because what happened is y was given, right? And then we are trying to find the derivative of y, which is, of course, f prime, right? And because y was explicitly written as a function of x, we call this differentiation explicit differentiation. That's all we have been doing so far. For the first time now, we are going to differentiate an equation that is not written in terms of y. All right, now why do we have to do that? Well, because sometimes some relations, some equations cannot be expressed as y equals something. All right, and that's why, and this, by the way, is going to give us a lot of information about derivatives of functions, all right, different functions that we have not seen yet. So here, okay, now, as I said before, we are going to cover a lot of stuff that appears in section 3.7, because once you have this wonderful tool called the implicit differentiation, we can do so many things in much easier ways. All right, so first look at this circle, the blue circle, which is x squared plus y squared is equal to 25. What does that mean? Okay, I hope you understand that this means that the radius is 5, right? Centered at the origin, and that is the circle that you see in blue. Okay, I'm going to pick a point here. Let's say this is 4, 3. Now, is this point on the circle? Yes, the Pythagorean triple, right? 3 squared plus 4 squared is equal to 5 squared, 25. So this point is definitely on this circle, which is why, by the way, I picked 25. It's a nice number because of the triple 3, 4, 5. All right, now this equation is not explicitly written in terms of y. If you are to find the derivative at this point, derivative of what? I don't even have an equation. All right, so maybe I should state what is the slope of this line L, which is tangent to the circle at the point 4, 3. You probably know the answer just from the geometry of the circles and the tangent line and so on, right? Because after all, this line here, okay, this black line is y is equal to what? It goes through the origin and goes through the point 4, 3. This is 4, this is 3. So the equation of this function, the line, is 3/4 x, right? So the answer is that this should have the slope. Remember how these two lines are related to each other? If they meet at perpendicular, which they do, because the green line is tangent to the circle, and we have this theorem that says the tangent line to the circle is going to meet perpendicularly to the line that goes through the tangent point and the origin. Okay, that's one of those things that the Greeks have discovered. Oh, I don't know, recently, like 3,000 years ago. But this green line L, the tangent line, has a slope which is the negative reciprocal of this slope. So the answer should be -4/3. Okay, so we could do this without calculus, of course. Or you can think of, now see, the circle itself is not, this circle is not the function, right, in terms of x, because it doesn't pass the vertical line test, okay? For the x is equal to 4, you have 2 points on the circle, namely negative and +3. So it's not the function, but we can make this into a function, just taking the upper half of this. So if you have x squared plus y squared is equal to 25, then y squared is 25 minus x squared. I'm only taking the positive half, or the y is always positive. So when you take the square root, you take the positive square root. And so it is possible to write the upper half of the circle as a function, y as a function of x. And then we can take the derivative, right? You know how to take the derivative of a function like this. What kind of a function is this? It's not a quotient, it's not a product, but it is a composition, right? The inside function is 25 minus x squared. The outside function is the square root function. So the derivative is going to be 1/2 times the blob, the inside function, raised to the power that's 1 less than 1/2, which is negative 1/2. Multiply this by the derivative of the inside function, which is negative 2x. And you can duly cancel the 2's. And so the answer to this question is negative x. And I'm going to write the denominator with a radical, 25 minus x squared, inside of the radical. And that is, that is the derivative of this function, y is equal to the square root of 25 minus x squared, which represents the upper half, the semicircle, the top circle, the top part of the circle of radius 5, centered at the origin, right? Now, if you evaluate this at x is equal to 4, because this point, x is equal to 4, and this is the notation I use. Not everybody uses this notation. I draw this long vertical line and then write the point where I evaluate this expression at. So this will be negative 4 divided by the square root of 25 minus 16. Of course, that's the square root of 9. All right. And so the answer, the slope of that tangent line, the green line, was, as expected, negative 4/3. Now, we predicted this from geometry, and that certainly works. So why bother learning implicit differentiation? Well, sometimes you can't do what we just did here, okay? Sometimes you have an equation so that no matter how you try, you are not going to be able to write y is equal to anything, right? So this time it worked, okay? But often you can't. So let me go ahead and write that. But often you can't solve an equation for y. All right. So in a case like this, you are going to do what is called an the implicit differentiation. Now here's the key. What do we mean by this? Right? Think of y as a function of x. Okay, so this is like y is like an outside function. All right, and so whenever you take the derivative of y, you're going to put y prime. And when you have something in front of y, then you do something else also. Okay, so y squared is actually y of x squared. So when you take the derivative, when you take the differentiate y squared in the process called implicit differentiation, this becomes not just 2y, but 2y to the first times the derivative of the inside, which is y prime. Okay, so I know this is kind of, like we've never done this before, but think of y as the outside function. And well, actually, no, don't do that. Think of y as y of x. It's a function. So when you have y squared, and when you have to differentiate it, it becomes 2 times y to the first, which is 2 times y. And then you have to multiply that by the derivative of the inside function. That's the chain rule, which is why we had to learn the chain rule before we learn implicit differentiation, right? Okay, so with that, let's go with that. We are going to differentiate every term of this equation. So x squared simply becomes 2x because that's the derivative of x squared. When you differentiate anything with y, you have to be careful and you have to insert that y prime. So y squared, as I said here, becomes 2y times the derivative of the inside function, being y. So it's y prime. Okay, now what happens to 25? The derivative of a constant is 0. Okay, and now we solve for y prime. First, let's divide by, divide everything by x, 2. So x plus y prime is 0. Y prime is negative x, and therefore y prime, which by the way is the same thing as dy dx, is equal to negative x over y. That's simple, right? And you say, well, wait, I have y in here, okay? And I'm not supposed to have y in my derivative. Well, that's true in explicit differentiation, because everything was written in terms of like y equals a function of x. But in in implicit differentiation, it's perfectly okay for the derivative expression to have y in it, because you already know what y is, right? In a case like this, y was 3. All right, so let's evaluate what is the 0.43 is what? Negative 4 over 3, which is exactly what we got, up here, right? So that gives us the slope of the tangent line, the green tangent line to the circle at the 0.43. All right, so this is what is called implicit differentiation. Okay, so I have this picture. What is this? All right, I should tell you at this point that you should, if you have a smartphone, you should download an app, a graphing calculator app. There are lots of graphing calculator apps out there, and most of them are free. The one that, and I'm not selling any of these. In fact, these are all free, so I'm not getting any commission. But the one I found most useful is called Good Grapher. Okay, so you can go to your app store or wherever you get your app from and look for Good Grapher or any kind of a graphing application, graphing calculators. That's something that you should have. In fact, you should maybe have multiple calculators on your phone. But this allows you, this app, Good Grapher, allows you to not only graph functions, y as a function of x, but I use this extensively in Calculus 3 because this app actually allows you to graph surfaces on in three-dimensional space. So that would be z as a function of x and y and so on. And you can rotate these three-dimensional surfaces and you can see them from the above and below and from different angles. It is a very, very useful tool. And it's free. I may have actually gotten an upgraded version, which may cost me, I think, cost me 99 cents more. But anyway, it's great. All right. It's the kind of tool that I could have only dreamed of. In fact, beyond what I could have dreamed of when I was an undergraduate student. Okay, so Good Grapher is one of those apps. You may find others. And by the way, if you find some great app, please let me know. And this is a picture that I drew of this equation here. What is this equation? All right, here's the second example, which is illustrated by this picture. The equation that the graph you are seeing is that of the equation x cubed plus y cubed minus 2y is equal to 0. It's not in the book, so you would not see this in the textbook. This is something I just came up with last night. All right, so what is that? Well, this is, it's an equation, but what is y? Y is equal to a function of x. Well, you can't solve this for just simply y because y is cubed, all right? And so you can't do explicit differentiation on this. Now, let's see, there is a point 1, 1 on this, right? 1, 1 is on the graph. How do I know that? Because 1 cubed plus 1 cubed minus 2 times 1 is equal to 0. This point satisfies this equation. And remember, the graph of an equation is simply the set of all points satisfying that equation. So 1, 1 is definitely on this graph. All right, great. 1, 1 is where? It's somewhere, maybe I can do this in red, somewhere around here. All right. And now what we will do is to draw a tangent line. Tangent line will be something like this. All right. Let's try to find the slope of the tangent line. Slope of L, as you see here. Okay, now how do I do that? At this point, oops, I can't write black on black. Let's find the derivative at 1, 1. And what I mean by that is not the derivative of y, which is a function of x. Right? What we have to find is dy dx. Okay, and of course I can just write this as y prime because that's what we traditionally do. But really, you don't have y as a function of x, so maybe it's better to write this as dy dx. Regardless of how you denote this, let's try to find this. All I have to do is to differentiate each one of those term by term. The first one becomes 3x squared. No problem, right? Plus, what's the next one? It's going to be 3y squared. It is, but remember, you have to multiply according to the chain rule by the inside function, which is y. Remember, because y is considered y of x. So that gives you y prime. And then minus 2y becomes what? 2 times, remember this, the derivative of y is y prime. So if you have 2x, simply that will become 2. But if you have 2y, then that's going to become 2 times y prime. Again, because when you differentiate y in implicit differentiation, then it becomes y prime. And the fact is, it's good to have y prime, because now, if you didn't have y prime, you can't solve for y prime, right? So now we solve this for y prime. Let's go ahead and do this. I'm going to factor y prime from the second and the third terms. So it's 3y squared minus 2, and then factor it out y prime. 3x squared is going to be written on the other side with a negative. And then simply, I solve this for y prime by dividing both sides by what's in the parentheses. Okay, there it is. That's an expression of the slope at any given point 1, 1 on this graph. Now, x is 1, y is 1. So all I'm going to do is to plug in 1 for x and 1 for y. And this is, again, the way I denote this. Evaluation at 1, 1 is going to yield negative 3 times 1 squared, and then 3 times 1 squared minus 2, and that is simply negative 3. Now, does it look right? Does the graph, does this graph seems to show that the slope is negative 3? Yeah, it does look like it. It's it's definitely negative because it goes from left top to the bottom right, and the slope seems to be about negative 3. So this is the correct, well, that's not why this is the correct answer, but it would make sense, and you can just verify this. Okay, now we are moving into the second part of the section on implicit differentiation. There you will see all sorts of things you can do with implicit differentiation, the kind of thing that we started to see in section 3.7.